Hi, thanks for joining me. Today I'm going to be going over problem 3 from week 2 of the Invariants Summer Puzzle Competition. As always, I'll leave a link in the description below to the Facebook page of the Invariants where you can find out more details about the competition. Anyway, this is the problem I have today. We have I1, I2, all the way up to IN being non-empty subintervals of 0, 1. So each of these guys are intervals which are subsets of 0, 1, and we want to show that this sum here over all pairs of IK and L such that IK intersect IL is non-empty of 1 over the length of IK union IL is bigger than or equal to m squared. So I've kind of introduced this cardinality looking notation, but this doesn't mean cardinality, this means the length of a set. So because we're looking at intervals, the length of, say, the interval AB, so easy would just be B minus A, and say the length of 0, a half, union 3/4, 1. So this guy here, this would be a half plus a quarter, which is 3/4, like so. Okay, so that's what we mean by the length of a set. Anyway, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the first thing we want to do is state and prove a quick lemma. I claim that for all intervals I and j, we have this inequality here holding that the length of I union j multiplied by the length of I intersect j is less than or equal to the length of I multiplied by the length of j. Now the way we're going to prove this, let me write proof, is actually quite straightforward. What we're going to do is just call this thing here A, call B to be the length of j, and then the length of I intersect j we'll just call C for now, like so. Okay, so we have A, B and C, and now by inclusion exclusion we can work out what this guy here is. The length of I union j is just going to be A plus B minus C, and the reason for that is because this set here has all the elements of I, all the elements of j, so A plus B, but we've double counted the elements that are both in I and j, so we have to subtract off what's in both, so the intersection, and that's C. So we have the length of I union j is just A plus B minus C. Now what we're going to do is consider the left hand side of this inequality here, and that is precisely this guy multiplied by this guy, which of course is just C times A plus B minus C. Now what we notice is this is a quadratic in terms of C, and if we just sketch it like so, it's going to have a maximum at C equals A plus B over 2. So if I just say A plus B over 2 is there, so the maximum, like that, say, whoopsie daisy, like so. It will look something like that, at least. It's a negative quadratic, and it has maximum at C equals A plus B over 2. But now notice that C we define to be equal to the length of I intersect j. And because I intersect j is a subset of I, and it's also a subset of j, it must be that C is less than or equal to A, and C is less than or equal to B as well. But in particular, that means that C must be on the left-hand side of this kind of maximum point. But we can actually do a bit better. We can say without loss of generality, A is less than or equal to B. Okay, because just by this thing here, the symmetry of the I's and J's, we can assume without loss of generality, A is less than or equal to B. So we might have A is there and B is there, say. But then, because C is less than or equal to A, if A is here, this point here, C is, say, there, but we notice that this graph here, which is a graph of this thing here, is an increasing function up to the point A plus B over 2. But in particular, it's an increasing function up to A as well. So that means that if we call this graph, say, f of x, the f of c, therefore, must be less than or equal to f of a. And f of c is precisely what we have here, and we claim that this is less than or equal to f of a, or we've shown that this is less than or equal to f of a. Well, f of a is just a times a plus b minus a, and that of course is ab, and that is precisely the length of I times the length of j, which is the right hand side of our inequality. So we get the left hand side is less than or equal to the right hand side, and that proves the lemma. Let me clean up the whiteboard and I'll continue. Okay, so we've proved our lemmas now. The next thing we want to do is introduce some functions. The first one is going to be hij, like so, and ij here are positive integers between 1 and m, so the indexes of our intervals, and it's going to be equal to just 0 or 1, so it's a characteristic function. It's going to be equal to 0 if ii intersect ij is empty, so their intersection is empty, that it doesn't contain anything, and it's going to be 1 otherwise, so if the intersection is non-empty, like so. Cool. pretty simple function. Next thing I'm going to consider is fi of x. And this is going to be from 0, 1 to the reals. Okay, and this function here is going to take on two values as well, but not 0 and 1 this time. It's going to be 1 if x is not in the ith interval, and it's going to be 1 minus 1 over the length of I if x is in the ith interval. Oopsie daisy, like so. So if x is in the ith interval, we're looking at the constant function 1 minus 1 over the length of I. But if x is not in the interval, then it's the constant function 1. Okay, so two kind of somewhat arbitrarily defined functions. Now I'm going to make a claim. Is that the integral from 0 to 1, let me put this down, of fi of x times fj of x dx, this guy here is less than or equal to minus 1 plus hij all over the length of ii union ij. So this is my claim, and it seems to be kind of plucked out of nowhere, but we'll see why it's important in just a second. Okay, now I'm not going to prove this claim, and the reason I'm not going to prove it is it's just kind of a long, boring proof. We start from this left-hand side here, which is an integral from 0 to 1, and what we're going to do is write that now as a bunch of integrals. So the integral over the intersection of ii intersect ij, plus the integral of ii without ij, plus the integral of ij without ii, plus the integral of what's left of this guy here. And then noticing how fi and fj are defined, we can just use these guys here, and it's just integrating constants, which is very nice. But then we have to use our lemma from before, and we just get a bunch of terms, a bunch of cancellations as well. But all in all, you can check that it does indeed give you this right-hand side. It's not too difficult, but just long and tedious, and I don't want to bore you with that. So for now, we're just going to suppose that this lemma is proved. Let me clean up the whiteboard, and I'll continue. Okay, so I've rewritten down how we've defined hij, and I've written down the exercise I left to you guys to prove. Now what we're going to do is notice that we have this inequality here is trivially true. The integral from 0 to 1 of the sum from I equals 1 to m of fi of x squared dx is bigger than or equal to 0. And that's clearly true because we're taking a sum of real functions, so that's going to be a real function. Squaring it, that's going to be a real function. Also, it's going to be a non-negative real function, and thus the integral will be a non-negative real number. So obviously that's going to be bigger than or equal to 0. Then what we're going to do is just use our definition of squaring the sum of things. This is going to be the sum from ij equals 1 to m of fi of x, fj of x, dx, like so. But because we're doing a finite summation, we can swap, and the integral is nice, we can swap the summation and the integral. So let's get rid of this, and swap them. Ij equals 1 to m, the integral from 0 to 1 of this guy here. Now, you can probably guess what I'm going to do next is just use our inequality, that this guy here, this integral, is less than or equal to minus 1 plus hij over the union of I union ij. Excuse me. So this is less than or equal to the sum, ij equals 1 to m, of minus 1 plus hij all over ii union ij. Like so. Firstly, let's deal with this minus 1 term. This is lovely to deal with because it's just a constant, and we're summing from ij equals 1 to m. Notice that there are mi terms and mj terms, so that's going to give us an m squared. So we get a minus m squared coming out here. So this is equal to minus m squared plus the sum ij equals 1 to m of hij all over ii union ij, like so. And now hopefully you can see we've essentially got the inequality we want to prove. If we bring this m squared onto the left-hand side, but we'll do that in just a second, and now focus on this summation term, hij is 0 whenever the intersection of ii intersect ij is 0, is the empty set. So we only need to focus when it's not the empty set. So if we just write this as a 1, and then change our indexing from to ii intersect ij does not equal the empty set. And now bringing the m squared onto the left-hand side, we get the inequality we want to prove. That this summation here is bigger than or equal to m squared. I hope that explanation has made sense. Thank you for watching. I'll catch you in the next one. Have a great day.